Using Newton's second law for rotation, remember Newton's second law for rotation is Newton's second law for regular motion, F equals ma, but it's turned into rotation. So torque equals moment of inertia times angular acceleration. So tau equals I alpha. So we can use a problem-solving approach for rotational dynamics that is similar to the approach for linear dynamics that we saw a couple chapters ago. So model that object as a simple shape and figure out what is rotating and what point does it rotate around. So what is your axis of rotation? Identify the forces that cause the rotation and draw a visual overview to clarify whatever it is that you're looking at. Then develop the visual overview by defining coordinates, symbols, listing whatever it is that you know, whatever you don't know. Identify your axis about which the object rotates, so your axis of rotation again. Identify forces and determine their distances from the axis. Calculate your torques caused by the forces and find the signs of the torques. Remember, positive rotation is counterclockwise. So then the mathematical representation is based on Newton's second law for rotational motion. We have torque net equals I alpha. I is moment of inertia. Find the moment of inertia I either by direct calculation or from the table that I gave you that gives common moments of inertia based on the shape of the object. And then use rotational kinematics to find angular positions and velocities, as we were doing earlier in the chapter. So the caber toss is a contest of skill in Scotland where they throw the tree, basically, a heavy uniform pole, landing it on its end. So we have a 5-meter tall pole, mass 79 kilograms, just landed on its end. So these people are throwing this thing. It's tipped by 25 degrees from the vertical, and it's starting to rotate about the end that touches the ground. Determine the angular acceleration. So that is the first part. Assume that the angular acceleration stays the same value, which is an approximation, but it gives us a good sense of scale for the problem. How long will it take the pole to rotate by 5 degrees? Okay, so the first thing we're going to do here is draw a picture of the pole. So we have the ground, and then we have the pole. Oh, that's probably way too much. It was at a what degree? 25-degree angle from vertical. So here is vertical. Here's our pole. This is 25 degrees. Okay, this is 5.9 meters tall. So let's choose a color here. This is 5.9 meters. Okay, and then we also know what?
The weight.
The weight. Where will the weight be acting?
Directly downward.
From where?
From the center of gravity.
From the center of gravity. So this is a heavy uniform pole, it says. So the center of gravity will be acting directly at the middle of the pole. So we can put that symbol on there, and then our weight vector will be coming straight down from there. Okay. Now, what we need to do with that weight vector is we know that torques apply in which direction?
It can go parallel, no perpendicular.
In the perpendicular direction, okay? So the weight is not applied perpendicular to this pole. So what we want to do is we want to break this torque or break this force into a perpendicular. There would be a parallel also, but that parallel is not going to do anything. So we would want a weight perpendicular to the pole. And that is going to be causing the torque that's going to pull this thing down. Okay, so we have this angle of 25 degrees, and that's going to come into play to create this perpendicular weight vector that's going to cause the torque. Does that make sense? Okay. So now we want to calculate the weight perpendicular. Where's that? How is that going to come into play?
Well, it's gonna be
What do you think? What angle?
it's gonna be 90 to the weight.
Okay, so if I complete this right triangle right here, we see the 90-degree angle hanging out right there.
Yeah.
Now, the only angle that we know here is the 25-degree angle from the vertical, right?
Um,
So where is that 25-degree angle in our little right triangle that we just drew?
it is going to be next to the center of gravity.
Is it next to the center of gravity, or is it down at the bottom of the triangle? Is the question.
I think it's next to the center of gravity.
If you just use geometry and parallel lines,
Oh, it's next to the weight.
this angle right here is the 25-degree angle. Parallel lines would mean that this angle right here is the 25-degree angle. And then also parallel lines would give us this angle right here is the 25-degree angle. Okay? So now that we know that, and I want to calculate W perpendicular, am I going to use sine or cosine?
Cosine. Wait, no.
With
It's sine.
it's sine. That's this angle here is my reference angle, and this side here is opposite that. So sine is opposite. So we're going to have sine 25 degrees equals opposite, which is W perpendicular over the hypotenuse of W. So that's our setup. So now W perpendicular equals W sine 25 degrees. Or I could write theta if I didn't want to write that just yet. So there's my W perpendicular. Now, what else do I need to calculate a torque? If this is my pivot point here.
Your force.
So my force is W perpendicular. I also need
Alpha or the omega.
I need the length,
Oh, the 5.9.
the distance from the pivot. So what is the distance from the pivot?
5.9.
It's not 5.9. Here's the pivot right here.
we go to the center of gravity?
And that force is being used at the center of gravity.
So,
2 point something.
Well, if I call the total length of the bar L, let's say, then the radius would be L over 2.
yeah, 2.95, I think.
Yeah, we can calculate that in a little bit. So then my torque would be the radius times W perpendicular. So then that's L over 2. And W perpendicular is W sine 25 degrees. But W is mg. So now we have the torque equals mg times the length over 2 sine 25 degrees. Okay, we know the mass, right? 79 kilograms. We know G. We know the length of the rod or pole, divided by 2, and then sine 25 degrees. So now we can calculate all of this.
How come the mg goes up top?
It doesn't matter how you write it. It could be 1/2 mgl sine 25.
Okay.
I just happen to write it like this. So I can write it like that. 1/2 times the mass, 79 kilograms times 9.8 meters per second squared. Length of the rod, 5.9 meters. Sine 25 degrees.
Okay.
What is it?
965.2.
965.2 units would be, we have kilograms, meters per second squared, so that's newtons. We have a meters hanging off to the side, newtons, meters. So that's correct for torque. Now, did we have to calculate torque?
No.
No, we didn't, but we had to calculate torque to calculate the angular acceleration, which we did have to do, right? So now what do we do?
Use one of our formulas.
Yes. So we know that angular acceleration, alpha, equals torque net over moment of inertia. We know that this is a rod.
But
And
it's
it's
going to be at a constant speed, so it won't have that.
no, it's not rotating at a constant speed. It's rotating at a constant angular acceleration.
Oh.
Okay. So it will speed up as it goes, as it falls, it speeds up. Okay. So we know this formula here. This is Newton's second law for rotation, right? So we just need to figure out the moment of inertia for this object. And this is one of those that was given to us in the table because this is a,
Thin. Is it the thin rod?
it's basically the thin rod, sure.
So.
So, and it's rotating about the end.
Yeah, so it's going to be 1/3 ml squared.
Okay. And we know the torque.
9.
So actually, if I jump back a little bit to where we were sitting right here, this formula right here before we calculated the torque, I should have done this actually. I have 1/2 mgl sine 25 degrees divide by, you said 1/3 what?
ml squared.
ml squared. The reason I just did that is because
Now the length doesn't matter.
the length actually didn't matter as much, right? The mass didn't matter though. The mass is gone. The length up top is gone. The length squared on the bottom is gone. We're just left with the length on the bottom. And so this has simplified. There's the 1/2 here and the 1/3 on the bottom. The 1/3 on the bottom flips and becomes a 3 on the top. So we wind up with, let me change back here. Alpha equals 3/2. There's a G on the top that sticks around. There's a sine 25 on the top. And then there's the 2 on the bottom, of course, but the L on the bottom still. Okay. So without having solved for the torque, we see a simplification. We didn't need the mass at all. So if you're doing a problem on the homework and there was no mass given, you'd be like, why was there no mass? Well, if you don't do any numbers just yet, you might see something like this happen, and that's why. Okay. So I wanted to show that just in case on the homework there's something like this. Okay, so now we plug the numbers in. We have 3, 9.8 meters per second squared, sine 25, divide by 2. The length is still 5.9 meters.
1.05.
1.05, significant figures, 2, so we go 1.1. Now this is alpha. Meters are gone. We're left with per second squared. So this will be radians per second squared.
Now we have to find a delta T.
Yeah, so how long will it take the pole to rotate by 5 degrees? So we know the angular acceleration is 1.1 radians per second squared. So now we just need to use a formula that would involve a delta theta because we want to go 5 degrees. So something with a delta theta. And obviously an angular acceleration.
This is very good. Right. Check that. Omega delta t.
Omega initial.
Oh, that one. Omega initial delta t plus 1/2 a delta t squared.
1/2 A or
Or-
alpha?
That is alpha.
Alpha delta t squared. Okay, now omega initial, this thing was just sitting there and then it started to turn. So omega initial is 0. So that term is gone. So we have equals 1/2 the alpha that we just calculated. And then we wanted 5 degrees. So the delta theta actually is the 5 degrees. But the problem is we're talking about radians here, not degrees. So we got to turn 5 degrees into radians. And then we're looking for delta t. So delta t squared here. So how many radians is it for 5 degrees?
We'll just multiply 5 by pi over 180. Right.
Are you reducing? Because you're in pre-calculus right now?
136 radians.
So there's 2 pi radians in 360 degrees, which reduces. You're right. So what do you get?
136.
136 what?
No, 136.
136 what?
136.
136th?
Yes.
What the heck is that?
Oh, do you want a decimal? 0.0277.
What? Okay, we want 5 degrees.
Yeah.
So 5 degrees. We want to get rid of degrees. So there's 360 degrees in 2 pi radians.
I forgot to multiply.
Yeah. What do we get?
Okay, so it's 5 times 2 pi. Oh, my calculator's made radians, doesn't it?
Doesn't matter if you're in radians or not.
.45.
0.087 radians. Okay, so this all is equal to 0.087. So now we want to solve for delta t. So we're going to multiply by 2, divide by 1.1, okay, to get delta t squared by itself.
We got a square root.
And then we'll square root both sides. So in the end, we wind up with delta t equals what?
Square root.
I don't trust you anymore, so I'm doing it too.
Okay.
Go ahead. We'll see. All right, I got an answer. Let's see what you got.
0.39.
Okay, so after significant figures, we will say what? Because it's actually 0.39 something, right? So we're going to round it. What do we got?
0.4.
Okay, so 0.4 seconds is the answer. Yes. So a flywheel is a big, heavy rotating disc that spins very rapidly with nearly zero friction. They're amazing. So also roulette wheels use a flywheel, sort of. They're not as good as these, but kind of the same idea. Just a big, heavy thing that keeps turning for a long period of time. So an electric motor spins up the flywheel, which continues to spin with very little energy input. When the system needs to provide power, the flywheel's motion is used to turn an electric generator. The typical system has a 540 kilogram cylinder with a radius of 0.30 meters. A small electric motor provides a constant 2.8 Newton meter torque to spin up the cylinder. If the cylinder starts at rest, how long does it take to reach its final spin rate of 13,000 RPM? What are we going to do?
I don't know. Is a picture necessary?
A picture is not necessary here. No.
No.
All we're going to do is draw a circle.
Yeah.
You know. So as long as we can understand what we're talking about, then what do we need to do first?
Okay. Well, we're going to be looking for an angular velocity, but it's in RPM instead.
Okay. Yep.
So we're for sure going to have to convert.
That unit right there is a bummer, so we got to convert that. How do we do that?
Multiply that by 2 pi.
Okay, so 13,000 rev per minute. Get rid of minutes and turn it into seconds. Minutes on top, seconds on the bottom. 60 seconds in 1 minute. What does this give us?
$216.66.
216 point stuff. So I'm going to write down 217, but we're going to keep our calculator's answer. This is 217 revolutions per second. But remember that revolutions is not a real unit. So really we have seconds to the -1. So we have our frequency in seconds now. Okay, so we want to calculate, you said earlier, the angular velocity. So omega equals this is a frequency that we have right now.
Alpha delta T.
We don't have alpha yet.
Yeah. Oh wait. Delta theta.
So we have the
2 pi
frequency.
radians times that.
2 pi times the frequency. We have the frequency. So this is just 2 pi. Oops, that's a pi. Times the 217 revolutions per second. So now we have, and revolutions isn't really there. We're going to wind up with radians. This is 2 pi radians times seconds to the -1. We wind up with what?
1361.36.
Okay. What is it we're trying to find here? What's the question?
The angular.
Well, how long does it take?
How long does it take to reach its final spin rate?
So, but we gotta find.
We have to find the angular velocity.
Okay. So right now we're sitting at what? 1361?
0.36.
0.3. Okay, so 1361 radians per second now. So we have omega. How long does it take is what we're looking for. So we're looking for delta T, right?
Yeah.
Okay. Now we have omega. What can we do with this? They gave us a torque.
Yeah.
Okay. So torque is 2.8 Newton meters. Okay.
Are we gonna need the mass of the radius?
No, because the mass will cancel out when it'll divide out.
Well, I don't know that for sure. I don't want to say that. So maybe.
I'll just.
Is it omega times the radius?
Omega times the radius.
No,
For what?
it's velocity.
Okay, we have a torque, right?
Uh-huh.
We have an angular velocity. So we can go a couple different directions here. How can I get delta T? Do we have any formula that allows us to do that?
Well, there's a delta theta omega delta equals omega delta.
Delta theta equals omega delta t.
We're not given the theta. That's the
We don't know how many times this thing goes around is a problem. So
Yeah.
maybe not that one. Maybe something else.
We don't have an alpha, do
We don't have an alpha? Not yet, but maybe we can calculate it.
Because this alpha equals delta omega over delta t.
Alpha equals delta omega over delta t. Because we have an omega and we know it started from rest. So we have delta omega. We could, if we calculated alpha, then we could use that formula right there, right? How do we calculate alpha?
That's the net torque over the moment inertia.
Torque over moment of inertia. So all we need is moment of inertia.
Oh, but you see, now this is a heavy cylinder with something in the middle.
Yep.
So it's going to have half mass times radius squared.
1/2 mass times the radius squared. Do we know the mass?
Yeah.
Do we know the radius?
Yeah.
Okay, we can calculate the moment of inertia then. So I equals 1/2 times the mass times the radius squared. So 1/2 times the mass is
540.
540 kilograms. And the radius is, where is it? Where is it? Oh, here. 0.30 meters, and that's squared. All right, so what's the moment of inertia?
24.3.
24.3. The units are kilograms, meters squared. Okay, so now we know the torque and we know the moment of inertia, so we can calculate angular acceleration, alpha, equals torque over moment of inertia. Torque was 2.8 Newton meters. Moment of inertia, we just calculated 24.3 kilogram meters squared. What do we get?
.115226.
Okay, so I'll write down 0.115. Now, what are the units here? If you look at it, the newtons, remember, are kilogram meters per second squared. So the kilograms divided by kilograms is gone. We have meters on top times meters, which is meters squared, divided by meters squared on the bottom, which is gone. And then we're left with on top per second squared. So our units here are something per second squared. We're talking about alpha. This is radians per second squared. Which makes sense because it's alpha.
Yeah.
Okay? And acceleration.
So then we're just going to divide that by omega.
So yeah, we have alpha and we have delta omega, and we're looking for delta t. So I want to rework that equation. So multiply both sides up here by delta t, and then divide both sides by alpha. So I have delta t equals delta omega divided by alpha. Delta omega, we calculated already. Oh, it started from rest. So the delta omega
Is the
1360.
would be final minus initial, so it's going to be positive. So we have delta t equals the 1361. Now you want to go back and find your calculator's answer for that. Radians per second divided by the calculator's answer here for alpha, radians per second squared. So obviously the radians per second divided by radians per second is going to be gone. And you're going to be left with, in the denominator, a per second. But in the denominator per second flips and becomes seconds in the numerator. So we get delta T equals what?
118.14.6.
11814.6
That's
seconds. Now that's a big number in seconds. So we want to be able to comprehend that. Also, we
3
want to use
hours.
significant figures.
Good.
Significant figure that, and it's going to be 11,800 probably seconds. And then we want to turn that into a more meaningful unit.
So divide by 60 to get minutes. Right?
Divide by 60 to get minutes.
196.
196 minutes.
Divide by that by 60 again.
Divide by 60 again. What do you got?
To get hours.
3 hours.
3.2 hours.
3.2 hours.
Gee, that seems like a long time.
Seems like a long time for a flywheel to spin up, but you get a tremendous amount of something out of it, right? We don't know what that something is called yet, but it's very useful. So
It takes 3 hours for you to get electricity. Like it. Is that what it's talking about?
kind of, yeah. It's very useful though.
I'm curious to know how flywheel does that what they mentioned.
All right. Constraints due to ropes and pulleys. So we dealt with pulleys a little bit ago. Here they are again. So we have this pulley, and notice the way that it's turning. We see this arrow here. It's going this way.
Negative.
So that pulley is turning in a negative direction. That's right. We have a rim speed. So the things that are moving along the outside of this pulley have a speed of omega r. We've seen that formula before. The rim acceleration is alpha r. That rope is not slipping. If it was slipping, we'd have a problem. Okay, so not slipping, this is an ideal situation. So the motion of the object must match the motion of the rim. So whatever this speed is up here, this box here must match that. Okay, hopefully that makes sense. So the velocity of the object is also omega r, and the acceleration of the object is also alpha r. Okay, so that's how we connect the motion of the rotation to the linear motion of the box as the wheel turns. So the pulley turns without the rope slipping. The rope speed, velocity of the rope, matches the speed of the rim of the pulley, which is the velocity of the rim. They're both omega r. If the pulley has an angular acceleration, the rope's acceleration of the rope must match the tangential acceleration of the rim. So acceleration tangential equals alpha r. The object attached to the other end of the rope has the same speed and acceleration as the rope. Therefore, the object must obey. Velocity of the object equals omega r. Acceleration of the object equals alpha r. Okay? Pretty straightforward. Hopefully that is logical. So Josh has just raised a 2.5 kilogram bucket of water using a Wells winch. When he lets go of the handle, the winch consists of a rope wrapped around a 3.0 kilogram, 4.0 centimeter diameter cylinder, which rotates on an axle through the center. The bucket is released from rest 4.0 meters above the water level of the well. How long does it take to reach the water? What do we do?
Well, we're looking for a delta T.
We're going to draw a picture
No.
this time. It's going to be amazing. So
Well,
we have
we'll see about that.
a cylinder.
Did you get it?
Looks like a rolling pin, but this is the thing that winds up the rope. So then we have the rope kind of getting spooled up around the cylinder, like so. And then the bucket coming down. There's our bucket. Okay. Now, what do we know?
We know that the bucket is 2.5 kilograms. We know that
Mass of the bucket is 2.5 kilograms. Okay. What else do we know?
the radius of the cylinder is 2 centimeters. So that's going to be 0.02.
Radius of the cylinder is 2.5 cent. Wait, no.
No, it's going to be
What did you say it was? 4 centimeter cylinder,
so 0.2 meters.
0.2 meters, 0.02 meters. Yeah.
Yeah.
Okay. What else do we know? What about the mass of the cylinder? Do we know that?
30 kilograms, or 3 kilograms.
3 kilograms. So mass of the cylinder, 3 kilograms. What else do we know?
The water bucket, so our delta X, or delta Y in this case, is 4 meters.
Okay. So up here, Y initial, 4 meters. And then down at the bottom, we have the bottom of the well, Y final, 0 meters. Okay. Also, what was the bucket doing when it was released? So velocity initial,
Would be 0.
0 meters per second. And velocity final,
Well, it's going to be 0 again, won't it?
no. When it hits the water, it's going some speed. We don't know what it is. How long does it take to reach the water? That's delta T. That's what we're looking for. Any other information that's not on here? No? We got it all? Okay. So now we want to take this picture that we just drew and turn it into what we've been doing. So notice the way that I drew the rope coming off of this. I did that on purpose because as this bucket falls, which way will this cylinder be unspooling?
It's going to positive way.
It'll be unspooling in this direction, which will be positive. Okay? I wanted it that way. All right? Based on the way that we're looking at it anyway, it'll be unspooling positive. Okay? So now when I go off to the side and I draw sort of more of a free body diagram, it's not a free body diagram, but more a picture like that off to the side, my cylinder has a center to it and it has a radius, and the rope is coming down like so, and that rope has a tension to it. And as this thing unspools, it is turning this way, which is positive. Okay? Now, as far as the bucket is concerned, let's draw a free body diagram for the bucket. Here's the bucket. What do we know?
It's going to have weight down,
Weight down and
tension up.
tension up. Now, is there a net force to this?
Yes, in the downward way.
Okay, so F net is down, which means I should probably draw the tension up a little bit shorter than the weight down, right? Okay. All right. So now I should do a sum of the forces.
So for each, though, correct?
Sum of the forces in the y direction for the bucket would be what?
Tension minus weight.
Tension up minus weight, which would be mg down, equals,
0.
No,
No.
because you're going to have.
there is an acceleration. So it would be what? Mass times acceleration in the y direction for the bucket. Okay, so now that there is an acceleration in the y direction for the bucket, that means that there is an acceleration for the rope on the wheel, right? On the cylinder. Agree with that? So now we start working our way backwards. So that means we have an alpha, an angular acceleration. So let me change colors here. Alpha equals torque net over moment of inertia. So now that I have that information, what is going to be the moment of inertia? Let's start with that one. Moment of inertia for this cylinder.
Oh, it's gonna be the 1/3. No, because it's got weight to it, so it's not hollow. The 1/2 MR.
It's the 1/2 mr squared. Yep. So we'll put that one on the bottom. Okay. Now, what about the torque net?
We're gonna have to solve for that.
Torque net, think about it.
That's just the mass of the acceleration.
All right, let's step off to the side for a second and let's talk about what's going on the wheel, or on the cylinder, I mean. So the acceleration of the bucket, okay? The acceleration of the bucket has to equal, if I go back up here, the acceleration of the object here is the block, right? Has to equal alpha times the radius of the wheel, but here's the radius of the cylinder. So the acceleration of the bucket equals alpha times the radius of the cylinder. Okay. So what do we have then? What does this equal?
Well, alpha is the torque net over I.
Alpha is torque net over
The moment of inertia.
the moment of inertia.
Yeah.
Okay.
Radius is
Torque net is just alpha over R.
Yeah.
So can't we just put the alpha over R in for the torque net?
So right now we would have the alpha is the tau over I, right? So we'd have 1/2 mr squared on the bottom times this r right here. We just got to figure out this tau.
Yeah.
Okay. So what's the tau?
The torque.
The torque. So how do I calculate the torque? Torque is force times distance away, right? Perpendicular force times distance away from the pivot.
So then it's R perpendicular.
It's what?
R perpendicular.
Well, no, because it's not a 1 bar, right?
It's the force applied times the perpendicular distance, or the perpendicular force times the distance. Either way. Okay? Look at how I drew that radius. I did that on purpose.
It's perpendicular.
It's perpendicular to where the tension in the rope is, right? So what is the torque?
R perpendicular.
R times
T.
T. Yeah. So torque net here is nothing more than R times T.
And
So-
then you can solve for T from the sum of the forces. Or do we already have a tension?
No, that's it. Like, that's it right there. So now let's simplify this up top. We have R divided by R squared. So like that would be done, right? Then the 1/2 on the bottom
Turns to 2 on the top.
becomes 2 on the top. So we have 2T on top and then MR on the bottom. Okay with that? Okay. So now I can take the 2T here over MR like so, times the r. Well, the r is going to disappear now. Okay.
So it's just the
Now, the acceleration for the bucket is going down, which is
negative.
negative. So I should have a negative AB, or I should put a negative in front of this to make it right. Agree with that?
Yeah.
Okay. So now we have equals negative 2t over just m. And that is not just acceleration of the bucket, but that's actually the acceleration in the y direction. Okay?
That's also going to be the acceleration for the cylinder, isn't it?
And that will be the acceleration for the cylinder because they have to be the same. Okay, so now I can solve for tension. So I can multiply by m, divide by negative 2. So I have tension equals negative 1/2 mass times acceleration in the y direction. Okay. So now what do I want to do?
Do we have to go back to our sum of the forces?
Yeah. So now in the sum of the forces, I now know what tension is. So I have this negative 1/2 mass acceleration in the y direction minus mass times gravity equals mass acceleration in the y direction.
You could,
So then solve for
This is a big M here. Big M. Okay. Sorry. Now I'm going to solve for
acceleration.
yeah.
acceleration in the y direction. So that means I got to get acceleration in the y direction on one side. So I might move this term over here.
Okay, but then you gotta also put 1/2, don't you?
I could multiply everything by 2. So let me do that. Multiply everything by 2. So that would be negative big M AY minus 2 mg equals 2 m AY. Now I'm going to move that term. So I have negative 2 mg equals 2 m AY plus m big M AY. Now I factor out the AY. So negative 2 mg equals, factoring out the AY, times 2m plus m, big M. Now divide both sides by this factor here, and I have AY equals negative 2 mg over 2m plus big M. And now I can plug all that stuff in.
So then the big M.
So could you divide out the 2 and the m?
I can't divide out the 2 divided by 2 here because there's not a 2 in the big M. And I can't divide out the little m's because there's not a little m on the big M also. So nothing can be divided out here. But I can plug everything in.
So A equals
negative 2 times.
The little m is the mass of the bucket and the big M is the mass of the cylinder.
So
Negative 2 times 2.5 times 9.8 divided by 2 times 2.5.
Yeah, and you wind up with negative 1.13 meters per second squared. Then we're going to use,
That's your magnet, correct?
that's the acceleration of the bucket in the y
Which is the
direction.
same as the acceleration of the cylinder.
Acceleration of the cylinder. So we have delta y now equals 1/2 acceleration in the y direction delta t squared. And now you can plug in everything and solve for delta t. We have delta y is 4 meters. It's actually y final minus y initial, so it's negative 4 meters. And that's where the negative sign comes into play. So then solve for delta t, and you wind up with 1.1 seconds.